Hello everyone, my name is Yahui Chen. Today I'm going to present the work MEUZZ Smart Sys Scheduling for Hybrid Testing. This is a joint work between Northeastern University and Stony Brook University. So currently we have two primary approaches for automatically testing softwares. The first one is fuzzing and the second one is symbolic execution. Fuzzing, um, its advantage is it's very cheap. We just randomly generate input and then run it with the tested program. Um, but its downside is it's kind of dumb because we cannot analyze the program on the test involved. Um, and concurrent execution is the opposite, which is costly because of the solver invocations. But it's smarter than fuzzing because you can analyze the program paths with more involved analysis. And hybrid testing combine the best of both worlds. It uses the fuzzing to explore majority of the program paths and then send the inputs of fuzzing to concurrent execution so that it can help bypass those program conditions that are hard to resolve. And here is the framework for hybrid fuzzing. As you can see, we have the fuzzing module, the concurrent testing module, and the coordinator module that will select inputs from the fuzzing seeds and then send it to concurrent execution to explore. So that you see there's this C selection that can be used to do this job. And the focus of this work is that we only want to explore how do we select inputs from the fuzzers queue to concurrent execution. So why do we need this scheduling in the first place? The reason is that concurrent execution is too slow to catch up with fuzzing, especially for large programs. To testify this hypothesis, we use QSIM, which is the state-of-the-art hybrid fuzzing framework, and it is optimized for fuzzing, and allegedly it's the fastest concurrent execution, and it runs this concurrent execution continuously. And to set up the experiment, we use 4 mid to small size programs from left to right and run QSIMs with for each one of them for 24 hours. And overall, QSIM executed on average only 25% of the inputs in the fuzzer queue. As you can see, the unexplored part of the seeds by concurrent execution is the majority. And there are existing works use handcrafted heuristics to select seeds. From the very beginning, Driller back in 2016 just randomly selects inputs. To QSIM in 2018 uses a few handcrafted heuristics such as the seed size or the creation time to rank the inputs in the fuzzer queue until recently DigFuzz in 2019 uses the path exercise frequency to measure which seeds has higher potential for concurrent execution. You know, these handcrafted heuristics, although they are simple and it's pretty quick when the coordinator wants to make a decision to select which input should be transferred to concurrent execution. However, they are pretty inflexible and ad hoc. Oftentimes, you cannot justify why we want to select inputs this way, and different programs often exhibits different traits that might or might not work for these heuristics. So simply put, there's no one-size-fits-all heuristics. And then we think machine learning can help us to address the problem. So here's an overview of how machine learning works, or supervised machine learning. Starting with the labeled data, we can extract the features and the labels. Then use some training model, we can learn the function f, which when inputs an x, which is a unseen feature before, and then we can compute y the label of the unseen data. So a very important problem or question here is why C scheduling is a good application for machine learning. We know that machine learning is not a panacea to solve everything magically. And in this specific case, we believe C scheduling can be learned because scheduling is based on feature importance. For example, the inputs with larger size tend to uncover more code in program P. Then the size is then the importance of the feature size is pretty high here. And the feature importance can be learned using data-driven approaches. Also, fuzzing conveniently will automatically generate large data samples for us to learn from. And another question is why we want to apply machine learning here for C scheduling. First of all, it's more scalable, and it is using adaptive strategy. Remember, we say there's no one-size-fits-all solution, so we need to learn this importance for on a program-specific way. And lastly, it's more general than empirical heuristics like the size, which may or may not work for some programs. And there are a few challenges if we want to integrate ML. So first of all, it's the manual workloads. How do we collect the data and how do we label those data? And what is even the label in this case? Also the efficiency, because traditionally training is really slow, but fuzzing needs to be fast. And this is the main advantage of fuzzing over symbolic execution. So we should not jeopardize that. And last part is the transferability. We want the learned knowledge be transferable from one program to another so that we don't need to start training from scratch over and over again. So we come up with MEUZZ. It's short for machine learning enhanced fuzzing. And the input of MEUZZ is actually the fast program as well as the inputs for the program. Then using this input, we abstract the features, and then we label the utilities. Again, using some kind of magical training method, we can learn the weight W here. This weight is specific to the fast program, but is it transferable to other programs? Which is what we want to learn, what we want to find out. Here are a few highlights of MEUZZ. Its feature engineering is very lightweight, so that it's very efficient and it's thus suitable for online learning approach. And its label inference is automatic, so no human effort is involved during fuzzing. And the last bit is the learning model will be transferable. So in the overview of MEUZZ, in this figure, it shows that for C scheduling, we follow step 1, 2, and 3. So starting from the fuzzer, it generates a bunch of inputs, and these seeds will be sent to our feature extraction module. And with the features, we applied our model to make a prediction. And then the highest scored inputs will be transferred to concurrent execution engine. And then the model training part starts after the concurrent execution engine generates a set of inputs following the seeds we provide to it. And we use what we call seed descendant tree to infer its labels. Now that we have features and labels, so we can use it to update our seed selection model, namely the model training part in step number 6. And this loop will continue with fuzzing iteratively. And it's important to know that the training and scheduling are done online and in parallel. The core techniques of MEUZZ are as follows: feature selection, automated label inference, and the last bit is the learning mode. And starting with feature selection, we create this following requirements for feature selection. As first of all, it should be learnable, so that it should be utility relevant, so that we can learn what features are more important. And also, it should be fast. That means the feature extraction needs to be lightweight. And the last bit is the learned model should be transferable. That means the features we select should be program agnostic. And here are a few examples of how of the features we select. The first feature is what we call bug triggering potential. It is the count of reachable sanitizer instrumentations. For example, if a input following base block B1 and B2, and we can compute statically the potentially reachable sanitizer instrumentations that, for example, are labeled capital B1 through B6. And then for this feature, we simply add up all this potentially reachable number, the number of all these potentially reachable sanitizer sanitizer instrumentations. And similarly, for co-covering potential, we use the count of the undiscovered neighbor branches. For example, if the seed following this branch B1, basic block B1 and B2, and we see that for this path, it has the neighbor basic blocks that are not covered before, and we can add up the number of those uncovered basic blocks, B1 and B2, as the co-covering potential. And also, since we are selecting or learning the importance for hybrid testing, it is very important that these features should be concurrent execution related. The first part being the path constraint modeling of concurrent execution is affected by the number of external calls or the number of indirect calls. Also, for symbolic execution, the constraint solving is a big bottleneck. So the features that are relevant are the number of comparison instructions and the number of edges in the path. And last categories of the features are those empirical ones that we extract from existing literatures or existing tools such as AFL. For example, the input size, or if it's the first seed that trigger new coverage. And it's important to note that all these features are very lightweight to extract. In our preliminary evaluation, we can extract 200,000 features per second on average. Thus, it's suitable for online learning. And the second highlight of MEUZZ's core technique is the automated label inference. First of all, what is utility? We define it as the potential to help fuzzer find more code and bugs. So to find out the utility of a seed, we create or we use a concept called seed descendants tree. For example, imagine this is the queue of the fuzzer, and the fuzzer imports 3 seeds from concurrent execution. And for each one of them, the fuzzer fuzzes these seeds and then saved the corresponding inputs that are valuable. For example, either these inputs, they find a new coverage or trigger a new crash, then the fuzzer will save them into the queue. And then we can conveniently use the size of this tree to determine how useful this originally imported seed was. In this example, we can infer the label for each one of them to be 4, 4, and 1. So the last bit is the learning mode. So MEUZZ supports online learning, which is the primary learning mode. It uses linear model. The upside of online learning is it doesn't need to store all the previous data, and you just update the model incrementally. The complexity of the updating algorithm is O of the D square. This is the dimension of the feature. And the other mode is offline learning, such as SVM or random forest and more. So offline learning has more sophisticated learning model. It's a more advanced than linear model, but the downside is that it needs to store all the previous data and return the model with the incoming data. So it's more time consuming. And the last bit of learning mode MEUZZ support is ensemble learning. It is simply the combination of different learning modes or learning models. This hypothesis is coming from machine learning conferences that normally ensemble learning has better accuracy than single learning mode alone. So for evaluation, we use these setups with fuzz MEUZZ with 8 real-world benchmark programs of various sizes. And we compared MEUZZ with state-of-the-art fuzzing solutions such as AFL, AFL Fuzz, QSIM, Angora, and Xavier. And here are a few research questions we want to find out or answer with our experiments. First one is, can machine learning-based scheduling better adapt to different programs? Second, are these models transferable? And the last part, also very important part, is how is the bug finding capability of a fuzzer powered by machine learning? First of all, let's just compare the coverage evaluation. We use one program, ObjDump, for this presentation purpose. So without C model initialization, which is starting from nowhere, we can see that eventually the machine learning based on MEUZZ take the lead in the code coverage. And the other graph here is the one that we fuzzed with model initialization, which we use an empty seed to start fuzzing. And I want to direct your attention over here. So without model initialization, originally we can see that MEUZZ is not performing well until here, almost 9 hours in fuzzing, and then it surpassed the traditional fuzzing technologies. And versus with model initialization, which we have this pre-trained model and use a different setup to fuzz, and we can see that MEUZZ can quickly outperform the other fuzzing technologies. So we think this is explainable because when we start without model initialization, MEUZZ will just randomly select inputs which will behave or perform badly until the model gets iteratively trained and adapts to the program being tested. So the coverage improvements over QSIM is about 10% to 27% in our testing data sets. And here is an important figure I want to share, which remember that we have the hypothesis that feature importance can be learned. And this figure shows for each of the programs we tested, this bluish range or shape is the initial feature importance that we just randomly initialized. And then this red or orange shape is the feature importance that we extracted after the fuzzing. So we can see that machine learning indeed can help us adapt to different programs with different importance for the features. Again, this reflects to our remark that there's no one-size-fits-all features. And here is another interesting findings. So after we aggregate all the feature importance for different programs, you can see that the importance of different features vary really largely for different programs. And the first thing we can see that the programs are sensitive to different features. Also, the queue size is the most important here. The queue size is the size or the number of inputs in the fuzzer's queue. We know that over time, when the fuzzer gradually build up the input queue, it is more and more difficult for it to find new inputs. So our seed descendants tree will grow more and more slowly, which is why the queue size is an important factor here. And the last bit, which is kind of surprising to us, is the new curve is the least important. And it is used by popular fuzzers such as AFL to prioritize the power spent on the inputs if like based on whether this is the input that bring in new coverage. And then for transferability evaluation, we conduct 24-hour testing with model initialization. And here's our settings. The baseline is compared with no model initialization. And then over the figure on the right, you can see the unit is the percent of the coverage change after we apply the learned model for initialization. And the x-axis is the initialized model, and the y-axis is the faster program. So for example, if we randomly select this square, that means, this one, that means if we're using libxml model, the model we learned from fuzzing libxml to initialize fuzzing campaign for fuzzing TIFF to PDF. And the increase of code coverage is about 4.4%. And in this evaluation, there are a few key observations. First of all, 38 out of the 56 cross-fuzzing settings are experiencing better results. As you can see, majority of the squares are kind of bluish. And some program is better with transferred models. For example, for readelf, you can see that when we fast readelf with whatever models we learn from other programs, it's experiencing significantly higher or co-coverage. And some models are very better received by other programs. For example, if we use TCP dump model to fast other programs, most of the outcomes will be positive. And also, we notice if we use the model learned from fuzzing other programs to fast TCP dump, we receive negative results. And our speculation is that TCP dump is the largest program in our data sets, and we potentially need more data to train its model. So we think that with more fuzzing to gradually improve the model, TCP dump will eventually experience better results. So the last bit of the evaluation is for the detected bugs. We apply all the programs, all the state-of-the-art fuzzers and MEUZZ to fuzz our benchmark programs. And eventually, this table shows the number of bugs found by MEUZZ. Overall, it finds 50 bugs, and 21 of them has been fixed. And there is one bug, one heap overflow in libtiff is found by MEUZZ only, and not by any of the other fuzzers. The conclusion of my presentation is that first, machine learning approach is more generalizable than human handcrafted heuristics, which are ad hoc and not generalizable. For example, the new cuff is really a empirical feature that we didn't know that doesn't generalize well. And also, MEUZZ is more adaptive to different programs. We see the increase of co-coverage from 10% to 27%. Overall for different programs. And the last bit is that the model demonstrates good transferability. We see that the transfer model improved 67.9% of the cross-fuzzing configuration, which is a promising finding. So obviously, our evaluation is based on very limited data sets, and this idea itself is interesting. However, the only way to test this theory is by doing more and more tests in practice. So we open source our code at this URL, and hopefully you can find this tool useful. And thank you for your attention.